Oop. Okay, we're starting with Rob now. Okay, Rob, the final few are trickling in here. So for our second workshop, we're going to hear from Rob Zellum. Many of you are familiar with the work he's done with Project Exotic and Exoplanets. And Rob, I think it was communicated, the goal is for everyone to do something. Okay, good. So you're prepared. All right, I'm going to turn it over to you and have at it. Thank you.
Cool. Yeah, thanks everyone for having me. Sorry I wasn't able to be out there in person. I'm on the West Coast right now. We're moving out to the East Coast, hopefully later this in mid-September. So I am now the Deputy Project Scientist for the Roman Space Telescope for communications. So basically I'm the science communications person for Roman. So hopefully I can communicate well enough to you all today. I'm also the project scientist for Exoplanet Watch. Hopefully you've heard tons about it, about Exoplanet Watch. If not, this is our citizen science project to observe transiting exoplanets, where a planet passes in front of its star, blocks out the star's light, and we can actually use this method to actually investigate the atmospheres of these planets using instruments like James Webb, like Hubble, and what our project is doing is helping us to basically schedule the time of these telescopes a lot more efficiently so we can get as much science out of it as possible. And you can actually do these observations with telescopes as small as about 4 inches. So relatively small telescopes that you can participate in this project. But we also have our own robotic telescopes in our network that you can use yourselves. So you can use telescope data that you check out from us or any other robotic telescope array in the world. And you can actually analyze your data yourself or with your students through Exotic. So let me share my screen. The first step that we're going to do is we're going to go to the Exoplanet Watch website. I can never remember our own URL. So what I just do is I just go in Exoplanet Watch. And that should hopefully be the very first thing that pops up on Google. Let me try that again. So there we go. If you just Google Exoplanet Watch or NASA Exoplanet Watch, you'll see what is Exoplanet Watch. You click on that to go to our main website right here. I'm on a VPN, so it might be a little bit slower for me. Apologies about that. But on our website, you can actually learn everything about our project. You can get to our how to get started page. You can learn about our team. You can sign up for our newsletters. One of the best ways to also keep in touch with all of us is to join our Slack channel. And I definitely recommend getting on our Slack channel. It's a great way to get in touch with any of us on the Exoplanet Watch team. It actually goes right to my own personal cell phone. So oftentimes it'll be myself or one of also our friendly users that help you out. So if you ever run into an issue, not a big deal, hop in our Slack channel and ask us for help on that as well. So usually to get started on this project, you want to click on how to get started. And then from here, we have this handy checklist on how to become an Exoplanet Watch participant or a watcher, as we like to call our users. So first off, you have to plan your observations and plan just sort of your coursework here. You can learn about exoplanets. We've linked here many helpful resources and websites and activities that you can participate in to basically learn how exoplanet science is conducted. Then you can make your own observations. And we actually have an observing guide for those of you who are lucky enough to have your own telescope or access to your own telescope. We actually have a little user's guide on how to do these exoplanet observations. But like most of you, myself, I request observations from our own network. Right now, our data is mostly coming from the Micro Observatory. This is a 6-inch robotic telescope in Tucson, Arizona, that they very kindly donated us their time to. And we have thousands of observations, about 11 years worth of data. And the Micro Observatory is observing almost every single night. So there's thousands of data sets that we need your help analyzing and reducing. So most of you will probably do request an exoplanet observation. And then once you open that tab, you can actually request one after you scroll by all this lovely legalese. You just enter your email address and prove you're not a robot by finding the cars in the the 3x3 CAPTCHA text. And then within a few minutes, you'll actually have a data set submitted and sent over directly to your email address. From there, you can then analyze your data. And this is the most fun hands-on part that I think of this entire project. It's also perhaps one of the hardest parts of the entire project as well. So for data analysis, you can actually use whatever telescope software that you want. AIJ is a very popular one that a lot of folks use across the community. There's also one called HOPS as well. But we've made our own Exoplanet data analysis tool called Exotic. And you can get to Exotic by multiple different ways. You can Google it, you can click on it here on our website. What I usually do is I go to our main website page, and then I click on the word Exotic, and that will pop you up right here, where you have 3 different options. So I always recommend that people start off with the beginner tutorial, regardless of how experienced you are with analyzing exoplanet transit or reductions in data sets. The beginner tutorial, which we'll do in a second, really gives us a really nice overview of what Exotic is doing and kind of what it's doing underneath the hood. Then if we have some time, maybe we'll head on to Exotic Standard. Again, I have a loaner laptop, so things are starting to crash when I was testing things out. So we'll at least get to the beginner tutorial. So I'm going to pause here for a second. I'm going to ask each of you to go to the Exoplanet Watch homepage, navigate to the Exotic homepage, and then navigate to the beginner tutorial. And while you're doing that, I'm going to drink some iced tea. All right, I'm going to assume that everyone's had enough time to get to the beginner tutorial. And I don't see Calais running up and down the aisle, waving her hand, arms frantically in the air. So I'm assuming that things are going okay so far. And if you do have any questions, make sure to bother Calais Talk. She's basically an expert on Exotic, and actually her students and her basically inspired us to make Exotic run on the Google Colab. So again, what the Google Colab is, for those who aren't aware, it's basically a way to run software, but run it remotely on Google's cloud servers. This is really great because your students don't have to download any software on their own computers. Everything runs on the cloud. You can actually run all of Exotic on your smartphone as well, or even a Chromebook. And it's really great for folks who don't have to worry about installing anything. Before we did this, I had Exotic on the Colab. I was getting questions, multiple questions a day on how to install the programs. This is a lot more streamlined. So in the beginner tutorial, there's lots of helpful text embedded into all of our notebooks. And so it'll talk to you about the steps overall of what the code will be doing here. So we'll be loading some telescope images. We'll be using our sample data right here. We'll then identify our target and our comparison stars, and then we'll run Exotic to generate our light curve. So we'll go from the complete data analysis of starting off with our raw exoplanet observation images, and then producing a transit light curve. So basically what you just want to do is just read the text here. It gives you full instructions. And also it basically, you're just play button a bunch of times. Each block of code also has an estimate on the runtime. So this block of code takes about a minute. And if it was real data or a real run of Exotic, it would take about 2 minutes. And basically what we'll do is we'll hit play here and start running off with the code. So you might notice if once we hit play, you get this warning. This notebook was not authored by Google. That's because we authored it ourselves. You can take a look at our very official email address, NASA Exoplanet Watch exotic@gmail.com. You click run anyway, and then the code will start running. Again, the code isn't running on your computer. It's running on a remote Google server. So you don't have to stress about that at all. But what this step right here is doing is it's importing a lot of software libraries that Exotic needs to run. So this is again great because it's being installed on that remote server. Nothing's being loaded or installed on your own local computer. And this can take a little bit of time, unfortunately, especially when I'm connected to both a Zoom and a VPN on a 7-year-old loaner laptop. So apologies, this might be a little slow on my end. But if you haven't already, click play right here for the very first step. Now, sometimes if you're like me and you're using a very old laptop, you might get this error message. It's fine. It's just telling you to restart your session. So you'll just hit restart session right here. And then we hit play again. And then it'll start it over again. And of course, nothing works live when you're trying to demonstrate it. Sometimes you'll have to restart the runtime session to get some packages to install, especially if you're doing it for the very first time on your Google account. Hopefully Clay can attest that after running this billions of times as she has, you won't get these error messages or these restart runtimes unless those Python packages have been updated. So what it's installing right now is a package called Bokeh. This helps us visualize some of the data a bit easier. This installed all of Exotic pretty quickly, and a bunch of other helpful utility packages like accessing the NASA Exoplanet archive. Here's some astronomy Python tools, some math and science packages, and some Google utilities. And it'll give you very helpful output on each individual step. It'll say, hey, I'm done importing these libraries. I've also automatically loaded all the sample data for you as well, which is really nice. It takes care of that for you in the beginner tutorial. And then it'll tell you when it's done with each individual step. You can also see if that step is still running by looking at the play button. You'll see like a little loading icon, like a semicircle that's moving. But here it's a play button again. You can also see the green check box on the left-hand side, just the left of the play button, letting you know that that cell is done running. And you also got that helpful email or that helpful message here that says you can move on to the next step. So now let's move on to step 2. Now, this step is arguably the hardest step of the entire data analysis program and project. It's basically you're trying to identify where the target star is and where your comparison stars are on the field of view. And it's basically just pattern matching. And this can actually be difficult for new users who aren't looking or used to looking at astronomy data. But also some of the microobservatory data you're going to get is naturally cloudy because that telescope is fully weatherproofed. So it observes every single night, rain or clear weather. So sometimes you'll just be very unlucky and get that, but such is ground-based observing. We also have in this also very, very helpful sort of user guides and also videos in some sense. So step 2A here actually has a video that steps you through how to determine a star's coordinates. You just hit play to expand it. Since I'm going to tell you how to do it, we're going to skip this really nice video. And we're going to go directly to step 2B. So what we have to do first is we have to select our telescope. This is a microobservatory sample data set. And our target here is HAPP32. And that we know that because it actually told us earlier in Exotic what the target was, like right here, that it downloads some images of HAPP32b, that our target star is HAPP32, and I think up at the top as well, that we're using this sample data set. When you check out data, you'll get a README file with all your data that tells you helpful information like your target name. And if it's not clear, again, or if you have any questions or if something doesn't make sense, hop on our Slack channel and we'd be more than happy to help you out. All right, so now we're at step 2B. We already have our telescope selected, we already have our target selected. So we're just gonna hit play. And Rob is going to pray that this works the first time. And it is, yay. So right here, what we're looking at is the very first in our data set. And here's a very helpful Finder field chart given to us by the AAVSO. So those who aren't aware, the AAVSO is the American Association of Variable Star Observers. They're the organization that is hosting all of our data and gave us, honestly, a few hundred of our first users. And they really have these amazing star charts that help more easily identify our target star in our field of view. Those who haven't done a lot of target star hunting, it's a pain in the butt, to use a technical term. But what you can do is you can read this sort of handy 3-step method on how to find a target star. You can also watch this video with some tips. My tip, what I do personally, is I try to look for big patterns. So here I sort of see this star, this grouping of 4 stars right here. I see these other bright stars nearby. So I'm sort of looking for maybe this sort of weird pattern right here, where we have the stars coming up and the stars going to the left. And if I look at my image on the left, I'll notice here's 4 stars that look eerily similar to these 4 stars. And then here, these 3 stars are potentially some bright stars up here. That third one might actually be off the image. So now that I have a rough estimate of where my target star is, we now have to do some more pattern matching to figure out exactly where our target star is. So you might notice that the AAVSO finder chart is not exact 1-to-1 with our field of view. That's not a big deal because what we can do, and this is the great thing about bokeh, is we can actually use the tools on the right-hand side of the image here to select some different tools. So if you click on this button, the one underneath the arrows, I can actually click and drag and zoom in on this region of the image. So I can actually click and drag to sort of focus on this field right here, this subset, to help me more easily find my target star. And then you can also use the arrow keys to move. You can also change with this button right here. You can sort of move in and out. We can also write on our image, we can draw a little happy face if we want. Revert everything back to the way it was, but for some reason it always keeps the happy face on there. Well, I don't know why. It just likes to haunt me like that. So what we'll do is we'll zoom back in. So again, I found this shape here. It's roughly here. And then if I look at my image on the right, I have those 4 bright stars that I just highlighted. I have star, star, and star. So one tricky thing about the AVSO finder charts is that it doesn't really show you as a dot the star that your target star is. It just replaces it with a little crosshair. So you don't necessarily know if your target star is super bright or super dim. That's the only bad thing about this AVSO finder chart. But I know that my target star relative to these 4 stars on the right, I could sort of find that the target star is going to be like in this triangle shape here on the right here in the center of the image. So I'm now looking for a little smaller triangle. So there's my 4 stars here. I'm looking for a triangle just the left of the 4 stars. And right here is that triangle. So there's my triangle on the right. There's my 4 stars on the right. So that means that my target star must be here. Then what I do is over it, and I write down those pixel coordinates. So that's 423.062. You don't really need the decimal points. Exotic doesn't care. You just need the nearest pixel number. So that's 423.286. And here in this box, it's asking you to enter the coordinates of this target star. And it's 423.286. And you have to make sure it's in this correct format right here, or else Exotic will have problems parsing it. You might get also some students that are concerned that they might have entered the wrong pixel coordinate, and actually a lot of our users are concerned like, hey, I accidentally put in the wrong pixel units or the wrong coordinates for my target star or even my reference star. Honestly, it doesn't matter. It's okay, because Exotic will check your work. So yes, we could conceivably automate this entire step by automatically picking out and identifying the target star. We really wanted to make sure that this project was participatory so that you actually went through the same steps as the data analysis code does, so you could fully participate in this project and understand what's going underneath the hood. All right, 423.286 in this format. And those numbers look eerily similar to the ones I just typed in on purpose. And then you just hit enter or return. Then Exotic will check your work. Sometimes it might not check your work here. It might not take until the next step, step 3, where it checks your work. But now we go to data entry, step 2 of 2, where we enter our coordinates for at least 2 comparison stars. So comparison stars, for those who aren't aware, these are stars that we're monitoring to help us divide out shared systematic error sources. So a comparison star ideally is a star that should nominally have a flat flux over time. Its flux will be constant over time. And any deviations from that flat line means those are errors that have been introduced into the observations of this target. And ideally,
Stop.
those errors.
Lost you for a second. We lost like about 30 seconds of your talk.
No worries. Where did I drop off?
On comparison stars, where they are.
Okay, perfect. So those aren't aware, comparison stars are basically stars that we monitor that help us remove shared systematic errors. So a comparison star in an ideal world is a star that has constant flux over time. So basically looks like a flat line if you observe it over time. And any deviations from that flat line are potentially due to systematic error sources, such as the target rising and getting brighter as it gets higher in the sky. And as the target sets, it gets dimmer in the sky. So you see this target go from bright or dim to bright to dim again due to air mass variations as the target rises and sets. And ideally, the systematic errors in the comparison star are also shared with our target star. So we can use our comp stars to map out our error sources and remove them from our target star as well. Ideally, a comparison star, a good comparison star, is at least as bright, if not brighter, than your target star. And ideally, it's a star that's close by. So here's my target star right here. I'm seeing by our smiley face, here's a good comparison star that's 326, 366. So just to make sure we match the format here, 326, 366. And let's pick out another star, and I'm cheating because the prompt has told me already. There's another good star at 416, 343, which is this dude right here. So we'll also type in 416, 343. And again, if you forget the exact formatting, it will tell you in the helpful prompts. Now, we chose a bright star and another brightest star near our target star. You could also select this star out here or this star out here. You also want to select a star that doesn't have a lot of companions nearby, because sometimes the flux of multiple stars can sort of enter our aperture and potentially skew our results. So I'd recommend you pick stars that are sort of have some separation between them and other stars. So all these ones down here would normally be good comp stars, but they're kind of far away compared to these smiley face stars over here. So that's why I recommended these stars as opposed to these stars on the bottom left. Again, though, Exotic will run through all your comp stars and it'll double check your work and it'll analyze your stars and pick up the best one. So again, no reason to fret about anything. And if you have any questions, ask us in our Slack channel. So I'll hit enter. Now Exotic has identified in our first image the location of our target star. It's now also identified the location of our comparison stars. And now we have enough information sent to Exotic for it to analyze your complete data set. So now we go into step 3 because our code tells us that we're done. We can move on to the next step. So now let's run Exotic to generate our light curve. Just like everything, we hit play on our Colab cloud. And then you'll start getting some really helpful output. So right here, this was importing Exotic, installing it locally on your own, on the Colab cloud. It was also checking our selection, our target star and our comparison stars as well, because it basically does a plate solution of our first image. It actually sends it off to astrometry.net, does a plate solution, and then checks your work for your pixel positions. It then runs through all of your comparison stars to pick the best comparison star, the one comparison star that produces the best fidelity observations, the one that produces the least amount of scatter. And then once it picks out the best comp star, in this case, neither of my comp stars were that good. Actually, using no comparison star produced the best result for this. It then fits our light curve. and it produces quite a lot of output sometimes. So this is doing a full fit to our data. And this step usually takes a few minutes to run. It's sped up a little bit because this is the beginner tutorial. Typically, this step can take about 3 to 5 minutes to do the entire fitting. So some of our more advanced users can run through from the very beginning to running Exotic in just a few minutes, if maybe not even a few seconds. Some of your students or participants might take a little while longer because it just takes them longer to make really weird smiley face figures and pick out their target stars and their comp stars in their field of view. Again, this part right here, identifying the targets in your comps, is the hardest part of the entire project. So if they can make it through that, they should be able to get to the next step. Then once you run on Exotic, it'll fit your data. And at the very end, it'll produce a fully analyzed and reduced light curve. So this is really the bread and butter of the entire project. Again, what this has done is this has taken our raw fits images, it's extracted the flux of our target star, the flux of our comparison stars, selected which of the comp stars to use, and then divided the target by the comparison to remove shared systematic errors. And what it's plotting out here, this is the flux of the target star with respect to time. So right here, there's the normalized flux of the target star. And then right here is where the planet starts crossing in front of the star, causing the star to appear to dim, casting a shadow all the way on the Earth, which is just mind-blowing that an exoplanet is casting a shadow out here on the Earth. So as it passes in front of the star, that star appears to dim. And then as the planet gets back out of the way, the star gets brighter again. So right here is our transit signal. Now, down here, we have this video to help you understand this light curve, but since I have some time and things haven't totally crashed on us, I can talk you through that really quickly. So what this light curve is telling us, not only is there an exoplanet here, but also is telling us a bunch of other helpful information, one of which is the transit depth. That's the dip in the light curve. As you can see here, the host star dims from a relative flux of 1 to 0.97. Or if you just take the difference between those two, 0.03 or 3%. So that means the area of the planet relative to its star is 3%. And then you can do some math by figuring out, if you know the ratio of the areas of these two things, you can also figure out the ratio of the radii of these two things just by taking the square root of them. You can actually figure out this planet is a Jupiter-sized planet orbiting around this sun-like star. This light curve is also extremely helpful because this tells us the mid-transit time, which is T-mid right here. The mid-transit time is basically a reference time. It tells us when this transit occurs. And this mid-transit time is what we need on our website and our project to help us schedule more efficiently exoplanet observations with Hubble and James Webb and other large ground-based telescopes as well. So these two numbers right here are the two most crucial pieces of information that we need out of Exotic and this exoplanet transit run. A great thing about Exotic that other software packages don't necessarily do is this is a fully scientifically motivated, statistically motivated fit to the data. So not only do you get a final answer, you also get the 1 sigma uncertainties from these values. So quite literally, your students can take a bunch of data from like LCO, from Microobservatory, from Skynet, from wherever. Take that data, analyze it with Exotic, and then in a few minutes, they can get a light curve just like this. Your students can then combine all the measurements together and publish your own paper where you've updated the transit time of this planet. And your students can publish in publications such as the JAVSO, that's the Journal of the American Association of Variable Star Observers. Calais students have published quite a few papers in the JAVSO, and now I think some of them are actually getting their degree in astronomy at some esteemed places like MIT, which is super, super cool. Congratulations to Clay and her students. And they can write their own first author publications, which is really, really cool. And actually, we really encourage students to lead their own studies. And you can actually do that from the transit depth here. and the mid-transit time. So I think I have only about 5 minutes left, correct? Yes? Oh, thank you. Sorry to make you run to the podium.
Any questions for Rob?
Yeah, happy to take questions. I can also go over our
It's almost ready.
results page.
Here we,
But what I-
here we go.
yeah,
Hi. You are exactly what I was hoping for from this conference. Because I would very
oh
much
God,
like
sorry.
No, it's good. You're okay. Just kidding. So I really love this. I love I just want to know how first of all, I've been trying to write on my own Python and this might be
Yeah.
a later question of because I'm getting errors with the pip,
Sure.
but how would we cite you in order because I know we would cite you and we would cite our data source to be able to publish like that. And I'm just wondering, what is your preference?
Yeah, it's actually the instructions on that are on our website. So if you right here, and once that loads through my VPN, right here on the right-hand side is how to cite and acknowledge our project. So looks like you're a little bit behind me. So right here, right-hand side of the screen. So basically, we just ask you to cite our paper and then add this acknowledgement section at the very end of the paper. You can also just Slack us as well and just ask us, and we're happy to step you through. But once your paper is published online, please let us know because we'd love to list it on our link, our list published papers. So down here somewhere are some by Calais students, for example.
You said this can be done with other people's telescopes? I'm sorry.
Yeah,
So people
yeah,
could
yeah.
use
So
their
this
own
should run on
telescopes and
any single
upload their
telescope.
images?
Exactly. Yeah. And we actually have a few hundred amateur astronomers who are doing this right now. And we've actually are working on getting an array of 9 telescopes and an observatory out here set up for this as well. We can also use LCO and Skynet too. So if you have time on either of those arrays, you can grab data from them and use Exotic to analyze the data. Also, you can just ping us and we're happy to sort of notify our users and get them organized to do an observing campaign. Our users love helping out as much as possible,
Crazy
and they'll
amateurs.
observe a certain target for you.
I have another question too. How well does this work if the planet doesn't do a full eclipse, if it only does like a partial eclipse, or you're at an angle?
Yeah, partial transits are also extremely useful. So some users will have uploaded their partial transits, and for new planets that we're now discovering for the very first time or trying to confirm, even partial transits are helpful. So what I always urge our users to do is to upload their data regardless of what they think the data quality is, because we have checks and balances on our side so that it won't sort of screw up our archive, our results page. But if you go to our results page, I'll just do this really quickly before we get to the next question. If you click on our results, you can actually see all the exoplanets that are already in our archive. So a few hundred, absolutely mind-boggling. I can't believe we already have over 400 targets and 6,000 data sets. Good Lord, that's nuts. But if we click on Happy 32, for example, this is the target that we just did in our beginner tutorial. What this will do is this will load up. Here is actually an O-C plot. I don't think I have too much time to go into this, but maybe if you buy Clay a beer at dinner tonight, she'll talk to you about O-C plots and what they mean. But here's our phase data. So this is all the data combined into a single light curve. So even a partial transit will be extremely helpful because we can phase it with other data sets as well. And you can actually go on our website right now and grab any of our data that you want. You can publish any of this data that you want. The only thing that we ask in return is you cite our paper, you add that acknowledgement that I just showed you on our pages, our website. And then if you show an amateur astronomer's data set, that you invite them to be a co-author on your paper. They do the work, they deserve the credit, especially if their data hasn't been published before. we make it pretty easy for you to collaborate and publish with them. You just click this link. It'll open up your Outlook or whatever email server you use, and then you can email them directly and they'll give you permission to use their data.
How do you
Hopefully that
download the
answered your
images?
question. Yeah. Oh, you can download the images right here. So the PDF, PNG,
No, the raw images.
posteriors, the fits of the data.
The actual images from the telescope, not the processed light curve.
So we do not host the individual FITS files on here because that would just overwhelm the database. So what we're actually storing right here and presenting is the time series. If you want to analyze FITS files or images yourself and do that through Exotic, you would have to go and request data from us. To get started, and then you click on request, and you fill out that CAPTCHA to prove you're a human and not a robot, and you'll get a data set emailed to your inbox.
So one quick question on doing the stars, like the calibrations. Are you supposed to pick ones that are numbered on the AAVSO thing, like ones that are numbered or ones that are not numbered?
I recommend picking ones that are typically numbered. Let me try to find that. The ones that are numbered are ones that have been identified as AVSO as being good comparison stars that are non-variable stars as well. So if you're unlucky though, sometimes there will be no comp stars in the field of view, and then you sort of have to fall back and select what you think is the best comp star. So I'd recommend typically using AVSO comps, but you can also use any star in the field of view. Exotic doesn't really care.
So one second, we have people reporting that the link to the Slack that is not working.
The link to the Slack is not working. Uh-oh. Okay. Well, then I will have to fix that link. Thanks for letting me know. But I can also copy the invite link. I can throw in the chat here, and then I can also send it to folks like I see Michael in the audience, and I see Clay in the audience. I'll Slack it to them, and those two can also hand that out.
That's actually what I was about to say. I was going to say, if you can't speak to Rob, I'm around. I use Exotic a lot, and Calais does. And if you can't get on Slack, I can add you in. And also, I do a lot of Exoplanet stuff with LCO and use LCO data. So if anyone's got some burning questions and Rob isn't here, volunteer to follow up.
And he will definitely help you if you buy him a delicious IPA for dinner as well. So
Test.
All right, unless there are any final burning, you have, one last question.
Yeah, my question is about the comparison stars. They're there as a calibration to give you a baseline. Okay, and you want to pick those that are constant. But what happens if you pick one and it's also got a transit going at the same time? What does that do to your data? And how would you know that that has happened?
yeah, so it'll basically inject an additional transit signal into your data. So I guess sort of taking a step back, if you use a star that's non-constant, like a variable star that has like star spots or maybe pelages, for example, that will change the star's flux over time. And that could actually induce changes in the measured transit depth. So if the star is very active yesterday, and I observed it yesterday, the transit depth could actually be a little bit bigger or a little bit smaller than it could be tonight if the star is not active. So that's why we want to look at stars that are ideally not active stars. And if there's a star that you pick as your comp star that also has a transiting planet that you just happen to be super lucky, it would also inject another transit signal on your target star. So what you can do is you can look at results on your light curve fit, and if something looks wonky or you don't understand, just send us a Slack message, bother Michael and Calais and in the audience if you want, and we'd be happy to help you out with that as well.
Yeah, so that if you get the light curve that looks completely normal, you're okay, but you might get ripples on it or something like that.
Yeah, exactly.
Okay, thank you.
All right,
Yeah,
we're going to wrap
thank
it
you.
up there. Yep.
Cool. Thanks everyone for having me, and thanks for calling in. Appreciate it. And hopefully see you all in our Slack channel soon.
Thank you, Rob. Appreciate it. All right, everyone stand up, stretch. We have one more